Alright, silly people, here's the situation. We have a triangular waveguide with side length A, and it's a right triangle. And we are meant to find the propagation modes for electromagnetic waves in this waveguide. So, um, starting with the TM mode, um, we are not going to try and derive the boundary conditions for this thing. Instead, we're going to make a symmetry argument, um, seeing that the triangle is just one half of a square, with the symmetry line being on the y equals x line. Um, we can just find that it is going to be the um, solution for a box, um, plus the solution, or minus the solution actually, of the reflected box, um, will be our longitudinal electric field. So um, the longitudinal electric field for a box is given by, well, pretty much the one for a rectangle in the book, um, except the denominators on the inside of both of these sine functions are going to match. So this is A, and this is A. That's the solution for a box of side length A. Um, and so on the symmetry side, flipping it along the y equals x line will make it so that this is now sine of m pi y over a, and this is n pi x over a. And so using our little relation up top, we find that the longitudinal electric fields in this triangular waveguide will look like e to the minus I omega t minus kz sum over m and n of a m n, and then all of this junk in here. So I'm actually going to write it on a separate line because this is going to get annoying really quickly. It's going to be sine m pi x over a, sine n pi y over a, um, minus sine m pi y over a, sine n pi x over a. Alright, that's your longitudinal electric field, and we can get all the other fields from that, so that's what we're going to do. The transverse electric field is always given by ik over gamma squared times the transverse gradient of the electric longitudinal field. So we're going to have to compute a gradient then. So without writing out, well, I guess I'll write out that the transverse gradient is just given by the partial derivative with respect to x times the x hat direction plus partial derivative with respect to y of the y hat direction. Just a gradient, but without the z direction, pretty much. So what that's going to look like is we'll have the t vector will be ik over gamma squared e to the minus I omega t minus kz. You have the sum of mn of amn. And then we're going to have to split this up into components. So x component is going to be m pi over a cosine m pi x over a sine n pi y over a minus n pi over a sine m pi y over a. And then cosine n pi x over a. Okay. And then that's the x component, so we are going to do the y component now, which is going to be n pi over a sine m pi x over a cosine n pi y over a minus m pi over a cosine m pi y over a sine n pi x over a. Okay. That's your transverse electric field. Then your transverse magnetic, as usual, is given by I omega mu t over k. And then you're taking the cross product of z hat with the transverse electric field. So that's going to change the constants out front, right? So it's going to be now minus omega mu t over gamma squared e to the minus I omega t minus kz, and then the sum over m and n of a m n. And I mean, now with the cross product, you're going to have the y component replace the x component, and the negative x component will replace the y component. So nothing too difficult there. So we have n pi over a. I'm actually going to factor out a pi over a so I can write this faster. Pi over a. So it's going to be n sine m pi x over a cosine n pi y over a minus m cosine m pi y over a sine n pi x over a. That's the y component, or the x component. Then the y component is going to be minus the x component from before. So now it's just n sine m pi y over a cosine n pi x over a minus m cosine m pi x over a sine n pi y over a. And that does it for the TM modes. Now we need to do the TE modes. So for TE now, we have to start with the longitudinal magnetic field instead. But thankfully, we can just make another symmetry argument, where now, with the magnetic field being perpendicular to the electric field, we're going to be adding the square forms of the waves with the symmetry argument between the two. So the solution for a longitudinal magnetic field in a square is given by e to the minus I omega t minus kz sum over m and n a m n cosine m pi x over a cosine n pi y over a. And then when you make your symmetry transformation, that is going to be just cosine m pi y over a cosine n pi x over a. So writing it all out, we have that the longitudinal electric field is given by e to the minus I omega t minus kz sum over m and n, a m n, and then cosine m pi x over a cosine n pi y over a plus cosine m pi y over a cosine n pi x over a. Okay. So then the transverse magnetic field is what we're going to get first from this, which, as always, is just ik over gamma squared times the transverse gradient of your longitudinal field. So we got ik, let me write an equal sign. We got equals ik over gamma squared. E to the minus I omega t minus kz. We got sum over m and n of a m n, and then we're gonna do x components and y components. So times, this is gonna be minus m pi over a sine m pi x over a cosine n pi y over a plus, or actually no, minus n pi over a cosine m pi y over a sine n pi x over a. And then the y component is going to be n pi, it's going to be minus n pi over a cosine m pi x over a sine n pi y over a plus or minus n pi over a cosine, no, that's a sine actually now, sine m pi y, so that means this should be an m pi y over a cosine n pi x over a. There it is. Okay. Finally, we can calculate the transverse electric field, which is going to be minus omega over k z hat cross the transverse fields. So that means we're going to have minus I omega over gamma squared e to the minus I omega t minus kz. We're going to factor out a minus sign from all this, so we're going to have a plus. And then we're also going to factor out pi over a. And you have the sum over m and n of the constant. And then the vector then, you're going to have the y component replace the x component, so now we have n cosine m pi x over a sine n pi y over a plus m sine m pi y over a cosine n pi x over a. and you'll have the minus x component replace the y component. So now it's just minus m sine m pi x over a cosine n pi y over a minus n cosine m pi y over a sine n pi x over a. So that's all the fields. So now we need to calculate what gamma and the frequencies are. So gamma, um, when indexed with m and n for the different modes, for a rectangle, is given by the, or actually for a box, for a square, it'll be over a squared and then n squared over a squared as well. And that's actually going to be the same sort of form for gamma for this situation, since we just use symmetry relations for the triangle. The gammas will be the same as that for square. So we can rewrite this. We'll have gamma mn will be equal to pi over a square root m squared plus n squared. And then the frequencies will be given by 1 over square root of mu epsilon times the square root of gamma mn squared plus k squared. And then, so we can plug in what we have for that. So that's going to be pi squared over a squared m squared plus n squared plus k squared. All right. So if you want to talk about what modes can actually exist in these formulations, for Tm, given the boundary conditions, the only possible modes that you're going to have are going to be for m is greater than n, it's greater than 0. And then for Te modes, you're going to have m is greater than or equal to n, greater than or equal to 0, but they can't be both 0 and 0 because that's the trivial case. So any of those modes are fine, but that means that the lowest mode for Tm is 1, or it's actually 2, 1. And then the lowest mode for Te is 1, 0. So we'll probably look at those in a minute. The next part of this problem is actually to calculate the attenuation constant, beta, which is the loss of the power on the walls. And it's given by minus 1 over 2p, p being the power, and then times the derivative of the power with respect to z, which is a funky little equation that doesn't really mean what it says it means. So let's just go ahead and start calculating the power. In general, the power will be omega k epsilon over 2 gamma squared times the integral of the square modulus of your electric longitudinal field over a area, right? So remember we got for our Tm mode, we had omega mn k. I'm going to be working in natural units, so I'm going to have epsilon go to 1. and then that's going to be AMN squared, and it's going to be the integral over x and y of, we're going to have the square modulus of our um, little guy here. So sine m pi x over a sine m pi y over a minus sine m pi y over a sine n pi x over a. And we're squaring all of that. And notice I got rid of the factor of e because both of them had like an I on it, so the square modulus will just go to 1. So we need to square this. We're getting a little bit into the weeds now. So splitting this into several integrals, we're going to have one of them with is just sine squared of m pi x over a, and then the integral from 0 to a of dy sine squared n pi y over a. You're going to have minus 2. These are the cross term integrals, so this is going to be dx sine m pi x over a sine n pi x over a, and then the integral from 0 to a dy of, it's going to be sine m pi y over a, and then sine n pi y over a. Finally, you're going to have the other squared term integrals, so those are going to be sine squared m pi or n pi x over a, and that's over dx, and then you're going to have the sine squared m pi y over a dy. And I'm going to use a little bit of a table integral. That is that the integral from 0 to a of sine squared m pi x over a, or actually just sine m pi x over a sine n pi y over a is equal to a over 2 times the Kronecker delta mn. Right? Dx dy. Or actually, they have to share the integration factor, so both of these are x, equals a over 2 del mn. So, looking at that, that means that we have for our integral a over 2 delta mm, and then also a over 2 delta nn, and then the cross terms are going to be a over 2 delta mn, and then a over 2 delta mn, and then plus a over 2 delta nn, and then a over 2 delta mm for all of those. And since we're doing this in the TM mode, remember we talked about what the modes can actually be. We're always going to have m is greater than n. So any Kronecker delta that has mismatched indexes will be 0. So in total, we'll have a squared over 4, a squared over 4, and so it's a squared over 2. All right, equals a squared over 2. Fantastic. So that means that the power then for the TM modes is going to be the omega 2, 1. I'm now just looking at um, the lowest mode. A squared k 2 over gamma 2, 1 squared, a 2, 1 squared times 1 half, because we divided it by 2 because I used the power equation for a square, and I had to take 1 half of it then. And then the solution was a squared over 2. So simplifying, we'll have omega 2, 1 k over 8 gamma 2, 1 squared, a 2, 1 squared. To get dp dz, notice that this power doesn't actually depend on z, so we'll have to get a little bit creative. So noticing that the negative integral, or the negative derivative of dp dz will just be 1 over 2 sigma delta mu c squared, and you're integrating over the power loss per unit area, right? And that's actually not per unit area, per unit like line that you draw around your surface, so unit perimeter, if you will. And because the triangle has 3 discrete sides that aren't really smooth at all, we're actually going to have to split this up into 3 different integrals. So that's going to be with the prefactor 2 sigma delta mu c squared, mu c just being the permittivity of the conductor surface. One of the surfaces runs from 0 to a, and the n hat direction is just minus x hat, so we'll have that guy integrating over y. And then one of the surfaces, this is the surface along the x-axis, is going to have an n hat equal to y hat, and then b naught, and then you're squaring it, and you're integrating over x. The other one's weird, and right now I'm going to write it like this, but the bound won't actually turn out to be physical. It's going to be root 2a because Pythagorean theorem. You're going to have the symmetric unit vector, so x hat minus y hat, and then crossed with b naught and squaring it. And then the line element becomes the square root of dx squared plus dy squared, right? So how I'm looking at this is we actually have a form for dy dx because the symmetry line is along the y equals x plane, positive or negative, it doesn't matter. So we can actually, from the line element, we can factor out dx, and then you'll have in the radical 1 plus the square of dy dx. And depending on how you're looking at the triangle, that's either a positive or minus 1, but either way it's going to square and make it positive, so it's just root 2 dx. And that's amazing because now we can turn that integral into just a dx integral. So what our power is looking like now, dp dz, is actually 1 over 2 sigma delta mu c squared, integral from 0 to a. You have just the modulus squared of by with x set equal to 0, integrating over dy. And then you have the square modulus of bx, integrating over dx, and you have now y set equal to 0. and then you have your silly integral from 0 to a, by minus bx squared, and you have y set equal to a minus x. That's how I did it, setting it equal to a minus x, because I'm looking at the triangle like this. So, I mean, if you wanted to flip it and say that it's x minus a, that would probably work as well. So, we have our work cut out for us. Remember, we found our transverse magnetic fields before, and we found that they were fairly, similar. So I'm going to go ahead and just plug them in, assuming that you've written them down. So, and also looking specifically at the 2-1 mode, because I don't want to make this general. Then those integrals are going to turn into, we'll have a dy integral of 2 sine pi over a minus sine 2 pi y over a. You're going to have an integral over x of sine 2 pi x over a dx minus 2 sine pi x over a squared dx. You're going to have from 0 to a dx integral, and this is going to be your really annoying by minus bx squared term. So that is looking like, well, you also have a factor of 2 out front, so let me write 2 dx. So you have cosine. Actually, no, there's not a 2 out front. The 2 is inside. Dx. 2 cosine 2 pi x over a sine pi times a minus x. Remember, that's what we set y equal to, over a minus sine 2 pi a over a minus x over a cosine pi x over a plus sine 2 pi x over a cosine pi a minus x over a minus 2 cosine 2 pi a minus x over a sine pi x over a, and then you square the whole thing. So at this point, I said screw it, because all this is just an absurd amount of trivial integrals. So I just plugged it all into a calculator, actually. And I'll tell you the result that I got. I got 5 pi squared times the fraction 2 plus root 2 over 2a. So that means that, remember, and that's going to be your value for minus dp dz. So plugging it all in, what we got for our p, and we're doing 1 over 2p, so I'm just going to write this out, is 1 over 2p dp dz. What we got for p, and multiplying it by 2, we'll have that beta is 4 gamma 21 squared over omega 21 k times 1 over 2 sigma delta mu c squared. You have omega 21 mu t pi over a gamma 21 squared. Square this thing, and then you multiply by your 5 pi squared. 2 plus root 2 over 2a. And yeah, all of those prefactors are coming from this stupid thing. 2 sigma delta mu c squared. Um, so yeah, that's what you're looking like. I'm not going to simplify it. You shouldn't feel like simplifying it either, if I'm honest. If you're asked if this wave guide actually has a TEM mode, the answer is no, uh, because the TEM modes are pretty much exclusively um, they're exclusive to coaxial cables. See, there has to be another conductor inside your waveguide for you to get those wacky TEM modes. So that's not a thing here. And pretty sure that beta, the attenuation constant, should be a property of the medium, not so much dependent on whatever wave you send through it. So I don't think beta will change if you calculate with the TE mode instead. You'll get the same thing. So yeah, have fun with that.